Hello, everyone, and welcome to the first modal webinar on of a new series we're putting together. We really wanted to connect more with our users live, be able to do conversations and chats and show some of the things we've been working on, and instead of just posting them on the internet into the ether. Um, I see folks have already started saying hello in the chat. I love to see that. Love to have an interactive webinar. Um, I see there's also people are already talking about where they're joining from. Would love to hear more. Um, I see some folks joining from Netherlands, Germany, London, folks in New York City, Madrid. Um, oh yeah, Cheyenne is excited to see that this is going to be a series. Yeah, me too. Um, Nativ joining from Israel, really great to see people from all around the world. Yeah, it's hopefully it's a nice day where you're joining from, whether that's India or Vancouver or Las Vegas. It's a nice but maybe a little gray day in San Francisco, but it's at least it's not 10 degrees like it is in New York, where some of my colleagues at Modal are joining me from. All right. So folks, the fact that folks are responding in the chat means AV is good. I think we're ready to go. So I'm going to start covering what we came here to talk about today, which is high performance LLM inference in production. So I actually have a really exciting announcement to share. Everyone here who is here live, you are the first ones to hear about this. Modal, the Modal research team partnered with ZAI to have day zero support for their new GLM5 model, which is currently available in ZAI chat and through Modal, and I'm not sure about anywhere else. Where I think the full announcement was scheduled for the exact time that this webinar started, so I think they might be sharing this as well at the exact same time. The model weights going up on Hugging Face, things like that, and yeah. So what I'm showing you here on this screen is an integration. I've been playing around with this model. I've been using it in my own agentic coding setup using open code. And this model has been good enough that I've been able to use it to build things, build the additional integrations. As soon as I got it running as like a command line interaction, I started using this model to write additional code to build a chat interface, to build the open code integration. Once I had the open code integration, I could really rip on adding features, and it's been really great. The model I have my own custom modal deployment in addition to the shared multi-user deployment, and it's like for a single user, you can get about 60 tokens per second, so it feels pretty snappy and fast. So it's frontier intelligence, and it is and running at the speeds that you get from the model providers. And yeah, I've no longer run into any API limits on my coding sessions. So we'll share the link in the chat. We have a demonstration of how to deploy this model on Modal and integrate it with a bunch of different front ends. We've got open code, OpenClaw, and the Vercel AI SDK. And we've also got a demo of how to integrate it with Claude Code. That one's a little trickier. That's actually why I prefer open code, not to go too far off on a tangent here, since we're talking mostly about the inference server and not the integrations in this webinar. But I do just want to shill open code for a bit. Open code is really great. It's sort of designed to integrate with other services, whereas Claude Code is really tightly tied to Anthropic. That's cool because they often will like ship new features really quickly. The integration with the model leads to like sort of like guaranteed performance and outcomes. And so there's nice things about Claude Code, don't get me wrong. But as somebody who wants to build like on open models and build open open systems, I really like open code's architecture, which is it's very cleanly separated into kind of like a back end component that's like a server that the front ends talk to. So like the terminal interface that you see in this demo here, that terminal interface right there is just sort of like it's very cleanly separated out as a client from the back ends, and that makes it really easy to sort of deploy a variety of different front ends of your own, or and like deploy it remotely, um, and and do like asynchronous coding agents. That's why Ramp used OpenCode on Modal to deploy their Ramp inspect um, uh, background coding agent. So yeah, big fan of OpenCode, and it's the primary way I've been consuming this model. Yeah, so you can find instructions. It's mostly configuration stuff. With OpenCode, we also show how to deploy on Modal if you wanted to like deploy the OpenCode server on a Modal sandbox as well. Okay, yeah, seeing some questions and things in the chat. So one was about inference engine choices. So both VLM and SGLang have day zero support for this model. So you can run it on either. A nice thing about VLM actually is that they support the Anthropic API messages out of the sort of out of the box. For SGLang, you can't do that. That's one of the reasons why Claude Code is a little trickier to integrate with. Most other sort of systems go through the OpenAI API compatibility layer, and SGLang has that, but it doesn't have the Anthropic layer. But so when the instructions that I have up at this GitHub repo show you how to do it with SGLang. The Yeah, there's some great differences between the inference engines. I'll save like a deeper discussion on that for the end, and happy to hear folks can post their experiences with those engines in the chat, like VLM, SGLang, what you've used. If you're using something else, would love to hear about that as well. There's lots. As somebody said, I think Levante in the chat, competition is always welcome. We love to see VLM, SGLang, Llama CPP, and others sort of like innovating and like pushing each other and making really high quality software infrastructure that we can use to take advantage of the really awesome open models that people like ZAI are putting out. So if you were reading the text on the in that GitHub screenshot, you may have noticed a free multi-tenant endpoint from Modal as a link down there. So this is a really exciting thing. Modal is like, we're a container company. That's what we've been so far. We help you run your code in the cloud. We help you run it on fancy big GPUs. We help you create big like fleets of sandboxes to run your coding agents in, or to like run evals in, and that's been the core of Modal. But on the Modal research team, we've been looking into what it would look like to have hosted endpoints on Modal, where instead of users deploying models, we deploy a model and we let you use it. So our first foray in this direction is our multi-tenant GLM5 endpoint. So all you need is to go to this GLM5 endpoint, modal.com/GLM5 endpoint, the link in the chat, and you can create an API key, and then you can talk to GLM5 FP8 quantization running on Modal. So this is we've been working a lot with people who deploy LLM inference in production and optimizing production inference that other people run. And we've learned a ton from doing that and working closely with customers and even running their endpoints for them. This is our first time that we've opened it up to everybody. So we're really excited about this, and we very much welcome feedback on what works and what doesn't, and how you'd like to like how you want to use it. Please try it out and let us know. The way we've set up this endpoint is first, yeah, it's free, and it will be free through the end of April. But when we'll like sort of look at what usage looks like and decide what to do next. The other thing is that the rate limit is one concurrent request. So I actually want to poke at this a little bit, because it's actually like different from I think every endpoint provider that I'm aware of. Um, so we don't have like a specific like tokens per minute or like uh, yeah, like limit on the level of like tokens in or tokens out, cache hits, something like that. We have a limit on concurrent requests. And I think that is like that's the way the most services kind of work. They work on in terms of like concurrency. And so I expect that to be the way, like as LM endpoints mature, I expect that to be the direction that they go. Um, but also this like the concurrency one limit is what we think is the best fit for using this endpoint with your like personal sort of like coding assistant or like home assistant OpenClaw setup. So like I integrate it with I live in a like big co-op house. We have a Discord bot running OpenClaw and integrate with this endpoint for that. And the like low concurrency is sufficient to handle like one or a few active threads of work, but like really like long context, full context, the model, which is in the like hundreds of thousands of tokens. And so I used to hit token limits a lot while using coding agents, and now I don't hit that. So you can get in touch with us if you're interested in higher limits, and we can work something out. But yeah, definitely still very much a sort of research preview experimental kind of thing. So there's a question from Cheyenne in the chat I want to make sure to get to. Can we integrate to open code through this endpoint? Yes, and we have instructions to do so on the GitHub repo that I shared earlier. It's called modal jazz, inspired by the I think it's Herbie Hancock quote. Yeah, the spirit of jazz is the spirit of openness, and we want this. We want to support the use of open models, open inference engines, and open um, uh, tooling to use to like make applications out of LLM inference. So yeah, uh, happy to support the broke students out there, to quote someone from the chat, who want to use GLM5 in their coding setups. So I want to pause. So from here, we're going to talk, like, I'm going to switch from kind of talking about this exciting day zero launch partnership and GLM5 endpoint to talking about like how to think about LLM inference and how to think about performance. So I want to like get take a moment to give people time to ask questions. Um, so let's see. So Thomas will question: will the traces be saved to create a large open data set for coding? We do not intend to train like to release the data for this. Um, yeah, I guess that's one to maybe check in on those with the sales folks to see what the exact policies are. but we would love to support open data sets. Not sure we can do that with this endpoint. Gabriel Gabber is asking average tokens per minute. Really depends on like input versus output, since our limit is on concurrency. So what that means is like you can drop many thousands of tokens of context, and we can, you can rip through the context, and it will at like thousands of tokens per second. And so that's on the order of hundreds of thousands to maybe even millions of tokens per minute of context. And that's distinct from the like decode throughput, which is like how many tokens of output can you get from the model. And so the output rate that we get sort of ranges depending on factors like the load on the replica and the success of the speculative decoding in guessing tokens. I would say the like range is 30 to 60 tokens per second per user. Let's be pessimistic and say 30 times 60, so it's 1,800 tokens per minute of output. So yeah, that's sort of the nature of serving on GPUs and kind of the nature of serving on pretty much any hardware that you have now. You're like the cost for decode is much higher than the cost for prefill. And so what happens, like to even further double click on this, what happens with an API endpoint that charges by the just like tokens with without like distinct limits on input and output tokens or distinct prices for input and output tokens, is that as an API provider, you have to kind of figure out what your typical workloads are, and then um, like figure out how many output tokens the model tends to generate in response to the queries you tend to get, and then you have to price it based off of that. Um, that's yeah. We find it like easier to reason about like how many users decode streams we have to manage, and that's controlled by this like concurrency limit. So again, if you're serving LM endpoints and you're thinking about how to think about capacity and how to think about load, the like request framing is actually I think better. And there's actually a blog post that I wrote kind of about this on the Modal blog, dollars per token considered harmful, that talks about this framing that you can check out if you want some more detail. Um, so Yuyo asking, how would you say your performance compares to other model providers for this and other models in the past? I'm going to assume you mean performance in terms of like speed. I've been trying to drop the word performance from my vocabulary. I know we have performance in the title here, but it's tricky because many people when they talk about performance, they think about model quality, because that's like the only thing that the proprietary APIs the proprietary APIs really center performance, right? Or sorry, model quality, because they're model builders like fundamentally, and they are competing on like frontier capabilities. So when they talk about performance of their system, they think model quality. But your question, since you say model providers, I assume you mean like speed in terms of throughput and latency. So we found that the numbers that I quoted, which is like 30 to 60 tokens per second per user, is in line with what the folks at ZII said we should aim for with our serving configuration. But we'll wait and see what happens on artificial analysis and other aggregators who compare performance. We expect also there to be a lot of really fast follows to speed up this model and run it faster, especially on B200s, because there's a lot of specialized kernels for this model, mostly shared with the DeepSeek v32, because the architectures are quite similar. There's things like DeepSeek sparse attention, the multi-head latent attention is also very DeepSeek-like, but there's still actually like quite a bit of room to improve these kernels on Blackwell. And we've been doing some of that work we have, various like patches, forks and Cuddy internal versions that use that and run faster. And we expect that to happen pretty quickly. So I would take the performance right now as like something like the worst it will ever be. Yeah. Um, I think I'll also answer the question that I don't think UEO was asking, which was like model quality, like how good is this GLM5 model? And I would say, in my experience, the difference between the two models I have the most experience doing this like open code work with, as opposed to just like a chat workflow. The two models I have the most experience with are GLM 4.7 and GLM 5, both in 8-bit floating point quantization. And in my experience, GLM 4.7 felt a lot more like using Claude Sonnet. And GLM 5 feels more like the using Claude Opus. So we have done some benchmarking, and some of our benchmarks, the model was beating Opus 4.6. Some of the benchmarks, it was closer to Sonnet. So I think there is this sort of there's a little bit of uncertainty. A lot of, when you have a model like released like this, it is a there's a lot of uncertainty and change. So I would expect the evals to sort of shake out um over the coming week or two on like crisply where it falls relative to both open and proprietary peer models. And I also expect that to kind of tease out a little bit per task. I think the focus of the model appears to be on agentic coding and sort of long horizon tasks. Those are also the hardest ones to benchmark. So we'll see exactly where it lands. Um, yeah, Yuio also asking about comparisons with Kimi K2.5. I would say, yeah, feels like a peer model, perhaps better for the long horizon coding tasks, but I don't have a ton of experience with that model. We don't have that or any other models available as endpoints, so that's something you'd want to deploy yourself. If you're interested in deploying that on Modal, come talk to us. All right, so I'm gonna switch gears here and start talking about what it takes to get LLM inference to run at high performance. A lot of this material is available in our LLM Engineers Almanac in this post on workloads. We've also got some information about like how to benchmark language model performance so that you can figure out how well you're doing on serving your workloads. So the key thing that I want to get across, if you take nothing else from this part of the webinar, just take this. It's that when you're running your own LLM inference and not just using an API provider, you have to get, if you want to reach the level of performance where you're matching or beating the proprietary, like what you could get from a proprietary model provider or a proprietary inference provider, you have to think about what your workload looks like. So this already came up when we were talking about like concurrency limits, token per second rates, etc. It's like once you actually run this yourself, you discover that there's actually some nuance that's being hidden behind an inference provider's API. And the like key division is in what the requirements are by the clients of your inference service on when they want results. And that usually depends on whether the thing waiting on the other side is like a human user in a chat interface, in which case you're serving like an online and interactive workload that's depicted in the middle. There, you care a lot about latency per user, token per second per user, also called interactivity by many people in the space. This is if you're building like like chat assistant. this is definitely what you're gonna want to look at. It's also pretty much very like the same interface, the same requirements that you have when building a synchronous coding agent. Then you have offline workloads at the kind of other end of a spectrum. Offline workloads are ones where there's like you get basically an inference job where you need to process a really large number of like prompts or inputs all at once. There's generally not any interactivity where the like outputs of the model go back to like an uncontrolled client for a response that then determines the next thing that you do. And each individual request does not have a specific latency requirement. The whole thing might have a latency requirement, like it might be a nightly job that needs to finish in 12 hours or 1 hour, but finishing, row 7 like within a certain number of milliseconds or seconds is not part of the requirements. And then in between, which is like kind of the most interesting set of workloads and one we're really excited about supporting with Modal, it's the semi-online workloads. So a semi-online workload kind of shifts between the two modes of online and offline, where sometimes the clients want a specific request solved quickly, and other times there's like a lot of work to do with a relatively loose latency requirement, and so you kind of need to switch between them, and you have very like highly variable load, a high like peak to average ratio of traffic. So we have users working on each one of these workloads, and this is where we've been able to get sort of reps in on figuring out what production inference looks like. So I want to talk about each of those to sort of give a little bit more color on what this looks like. So our like prototype user workload for production workload for offline inference is Weaviate's database transformation agent. So this is a sort of preview feature of Weaviate where you can, as they say here, augment and improve your entire data set with a single prompt. So you have some information in a database and you want to take all the like rows in a table and you want to like maybe join with some other table and then produce a result using a language model. So in this case, this is more like an analytic database action, right? It's more like OLAP or something you might do with Snowflake, Redshift, what have you, where you have a whole bunch of things you want to scan an entire table, basically, and produce a result from that. So this is very much an offline workload because like the job's not finished until everything is finished. And yeah, in these workloads, your concern is about like throughput of finishing requests. We have found that there's like frequently, especially for models at the like 8B scale or so, a slight edge to VLLM in throughput. So that's the inference server we recommend for these workloads. And if you check out the workloads doc, you'll see more detailed recommendations and some sample code for running an offline job. The sample job there is taking every day's SEC filings. So the federal government shares everybody who filed information of a legal insider trade. They put that out every day, and we summarize those documents and run that at like I think 30,000 tokens per second per GPU on a small model. So yeah, so these that's the like offline class of workloads. If folks have like, we'd love to hear if anybody has offline workloads that they've run. Maybe another one that's kind of sexy these days is uh, uh, reinforcement learning from AI feedback or reinforcement learning from verified rewards. You want to roll out inference on a giant batch. You don't really care how quickly any individual element of that batch finishes because you're going to take those and you're going to use them to do training and fine tuning of the underlying model. Yeah, so it also has this offline shape, and we've seen folks like Scaling Intelligence, a lot of research labs doing this kind of work. Yeah, so if you have a workload like that, would love to hear about it in the chat and also answer any questions. In the meantime, I'm going to go through the other two workloads and then answer questions about all of them at the end. So online workloads, I think people who've used ChatGPT or the Claude chat AI UI are familiar with these. You um, you want very quick response to each individual request. So our sort of prototypical customer for this is Decagon. There's a case study about this available on our blog that talks about the sort of things that we in Decagon did to achieve ultra low latency. Um, and this is for their Decagon voice. So this is a voice interface, which includes language modeling as a component, because the input is spoken language, the output is spoken language. And this is a customer support use case here. So again, there's like one person, they're on the phone, you want to get back to them pretty quickly. You're driven by essentially the pace of human conversation, which means responses need to come in at about human reaction time, which is in the low hundreds of milliseconds to like about a second, that you get that first sort of like byte, that first token or that first audio byte back to the user. These also, unlike a lot of sort of offline workloads, there's you get one input, you respond to it, and then you get a follow-up input for that same session. So there's like a stateful client, a human maybe, on one end, and you need to sort of like maintain that state over time. So that's depicted by those like lines in that figure on the left. So it's showing like an extended session. So we'll go into a lot of detail about how to improve latency, since that is the one where there's both the most existing work to talk about and sort of like the most knobs and things that you can turn and tune with both infrastructure like Modal and inference engines like SGLang. So we'll talk about that in really great detail in a second. So then the last class of workloads, semi-online workloads, are sort of flagship example for this. Customer for this is Reducto. They do document processing. So you put in documents and you get out sort of like structured extraction of information from them. The client on the other end is frequently a database. That database might be an analytic type database where you're doing like occasional queries on like the status of your business, on like customer retention or whatever, or it might be one where might be a transactional database that's participating in something that is less interactive than a chat. So like a user's going through an onboarding flow and they're like setting up a bunch of documents that needs to get processed by like a longer pipeline of jobs, where LLM inference is just like one of those jobs. And so the time scales for these tend to be on the order of many seconds to minutes. And the load tends to change a lot. So that's depicted in that chart by switching between these like big blocks of like one or a few requests to a bunch of requests, these like little blocks in the middle. So that's like at one point you have like one or a couple users dropping a few prompts in or dropping a few inputs in, and then you switch over to a like somebody drops like they just say like, okay, please index our entire notion for our whole company right now. And they don't expect that to happen in 400 milliseconds so that they can immediately like action on it. They want like they're like constructing like an index. And that so that looks a lot more like the offline jobs. And so the key thing you need to care about here is flexibility in scale, the ability to like switch between like relatively low latency for some queries to super high throughput for other kinds of queries. And there, Reducto and others have found that modals like GPU snapshotting and other features for really fast auto scaling are really critical for um, yeah, for achieving their SLAs and making their customers happy. Cool. So question in the chat from Kevin, do offline workloads have on average lower cost per response than online workloads? What are the cost breakdowns for these three workload types? Yeah, I would say offline workloads tend to have a lower cost like per request or per token. If you think about these like the individual request, like one of these lines in this bar, like one database row. So if you were to go apples to apples, the like total number of LLM inference forward passes for an offline workload and the same number in an online workload, it's generally going to be a lot cheaper for an offline workload. So this is also, I would say, an opportunity to flex your muscles as as an engineer and come up with clever ways to transform what looks like it like must be an online workload to an offline workload. Is there a way that we can like do this work offline ahead of time and make it a ton cheaper? And then the user will experience much lower effective latencies, but then uh, our system can operate with much looser latencies, and so we can choose these like performance optimizations that reduce our total cost. There are many reasons for that. I think it's kind of like it's almost like inherent in offlineness. It's like shows up all over the place in computer systems that the offline version is like cheaper and and more robust and easier to engineer than the online version. It's also very much a feature of the hardware that runs language models. GPUs, they're like very much throughput oriented machines, and so they can achieve super high throughputs really easily. And I think it has been challenging for anybody to come up with hardware that can handle the load of large scale LLM inference at low latency, um, any more effectively than a throughput oriented system like a GPU. Great question, Kevin. And I see more questions in the chat. Really appreciate that. Love to keep this as interactive as possible. So, question from Aryan: how is batch size tuning tackled in semi-online workloads? In online, it's usually dynamic and smaller batch sizes, and offline workloads is max batch size generally. So, how do you tune for semi-online? Yeah. So what I would say is that this is one where the sort of infrastructure around kind of like auto scaling, load detection that Modal provides, or that you would need to build yourself with like Kubernetes or Dynamo or whatever, that becomes really critical in the semi-online workload, because Ariane is spot on. In online, you go with the smallest batch size that you can afford, to get a really, really fast experience. There's nothing like giving every user the GPU for the entire time that their request is running. Um, and and then you maybe like dynamically adjust it in a small range in an online workload. And then with offline workloads, you just want like this big offline workload, these big batches, is exposing a ton of parallelism to you as an engineer that you can then take advantage of like all the way through your stack down to the hardware. For semi-online, you have to be able to kind of switch between these two modes. And the current state of inference engines is a little bit short here, which is that it's not easy to dynamically change some of the configuration knobs that you need to tune that go between sort of like online, like more online focused optimizations and offline focused optimizations. It's things like, the CUDA graphs look different, the kernels that you use look different, and like a bunch of other choices the inference engine needs to make. And right now, the answer from the inference engines is like, okay, you're serving a different workload, just like redeploy. You can also, like, you could maybe like sort of deploy different copies of the engine with different properties once you're at a sufficient scale that you can sort of like keep all of those running. Or if you can boot them fast enough, then you can sort of like intelligently route between them. So that's one thing that auto scaling or sort of serverless resource management system like Modal can really help you with. The other piece is that with semi-online workloads, what you need to do is not like choke and go down when the like request load suddenly goes up and you have one of these like big larger jobs to handle. You need to like burn through that queue. You need to queue it and then burn through that queue as quickly as possible. So this like a sort of narrow suggestion inside of Modal is to set a sort of target inputs per container at a certain level that is acceptable for all of your online requests, and then set a max input that's like the maximum batch size that you want to tolerate during like batch inference. And what Modal will do in that case is we'll queue up all these requests that come above the limit for take that limit, multiply by the number of replicas you have up. We'll queue the requests, and then we'll start spinning up additional replicas to rip through that queue. And that works really effectively. And Reducto talks a lot about sort of queuing strategies in this case study that we have linked. And yeah. Yeah, I think that covers everything for semi-online workloads. Yeah, and yeah, in our experience, the inference engines handle that kind of like dynamic batch size stuff relatively well across a couple orders of magnitude. So a question from one follow-up question from Ariane. Thanks for your insights. Timeout-based batching to keep some SLA, drain the queue. Yes, great summary, Ariane. And okay, from another question from Ryan. Have offline workloads mostly stabilized now that engines like VLM can keep GPUs saturated with batching? Are there still major open problems in throughput optimization? Yeah, so throughput is, closer to solved, I would say. Yes, in that there are, at the very least, it's like really easy. I think we report like 99% plus GPU utilization for our throughput demo. The one shared in the workloads doc. Um, the there's a little subtle caveat to that, which is that's how much time does a kernel spend running on the GPU, which is not the same as like how effectively are you making use of the GPU's resources. That is that's not the utilization reported by NVIDIA SMI or available in the like modal uh, dashboard interface. That's that's like lower level utilizations like streaming multiprocessor utilization, and even lower level like total like tensor core flop throughput utilization. So we also have a blog post for that one, the GPU utilization guide. If somebody could share that blog post in the chat, because I think a lot of the people in this webinar would really enjoy that one. That sort of talks about all these different layers of like how effectively are you utilizing your hardware. So the first layer is pretty well solved with throughput, with open source engines and on the models that they support. But the lower levels are like there's maybe some additional work to do, especially for GPU, especially for Blackwell GPUs. They're a little fresher. There's fewer really good kernels for them. We've been working quite a bit on that ourselves as well, which I'll share a little bit later. Pia Solomon in the chat asking about GPU power usage. this is in the guide, so I wasn't going to mention it, but since somebody in the chat mentioned it, like with most ways of sort of visualizing GPU utilization, it's really easy to get this NVIDIA SMI utilization metric, or but not the lower level metrics. They access privileged performance counters, and not every cloud provider offers that access to those. If you are if you're serving production inference and you do need access to those performance counters, you can talk to us at folks on our limited number of folks on our enterprise plan can have access to these performance counters, but you actually don't need them. Is my maybe like a controversial take. You, as Solomon indicates, there's GPU power usage, which is like what fraction of the total power draw of the GPU are you using? And NVIDIA's hardware is like power limited, and pretty much all computer hardware, when you really push it, like power ends up being your bottleneck. And that's not privileged information. It's like really easy to get a hold of. We share it in the in our dashboard, and that's what I use as a almost literal temperature check on like how effectively is this resource being utilized, and that captures problems like communication deadlocks and things like that show up really clearly in reduced power usage. So that's my like one of my little performance tips, I would say, is like monitor your GPU power usage, and if you're pretty high up there, then you probably should focus your optimization not on the GPU level, but on other ways that you can sort of optimize performance. Really excellent questions. Actually, I was surprised that I prepared a bunch of material in case nobody asked any questions. So I'm going to have to go really quickly through this sort of performance optimization material on like optimizing for latency. So I'll go through this really quickly. Slides are available, and a lot of this material is also in the workloads doc, so you can follow up there if anything is unclear. So the key question that you want to ask in performance optimization is, why isn't this faster, right? Hopefully you eventually get to a limit which is like, it's really expensive to make new semiconductors, and it takes a long time to make the hardware faster, and that's our limit. But you need to sort of like repeatedly ask these why questions until you hit those like fundamental limits, so that you can make sure you're doing everything you can as an engineer to achieve the maximum possible speed. So this is a question we ask ourselves at Modal about everything from like launching blog posts to like running kernels. So I'm going to start talking about all the different sources of latency that you can see, that things that feel slow, and that you wish were faster when you're doing LLM inference, when you're serving it yourself. So the first one is token latency. Why aren't we getting tokens faster? So one of the key low-hanging fruits here is just don't block the GPU. The GPU is the like coprocessor that's doing the hard work. It's driven by the CPU. The CPU decides what work needs to run on the GPU and sort of issues it. And you want to make sure that you are like never blocking. So if you do like a trace with something like the PyTorch profiler, you'll see these like blocks in your CUDA streams where no GPU kernels are running when the CPU is like, when they're waiting on something from the CPU. So we worked with the SGLang folks to improve to reduce GPU stalls that we observed. And you can read about some of like both like the high level concerns here and some of the specific like nitty gritty fixes that we did to remove host device or CPU GPU syncs. The key signature that one of the key signatures that you might have: host overhead. If you have enough work to fill the GPU, you'll see low GPU utilization in the modal dashboard or an NVIDIA SMI. That number directly reflects this like the fraction of CUDA stream gaps that you have. So that's a really great way to pick this up. So that's like really straightforward thing. Just like make sure that the GPU is always doing something to move things forward. The tricky bits are things like speculative decoding and like grammar-based decoding and those kinds of things sort of complicate ensuring the GPU is always fed. The other, so that's like, you don't need to know that much about what's going on inside of a GPU or inside of LLM inference to sort of like figure this out and to fix this. So if you're sort of a systems engineer, this is a place where you can contribute to the open source inference engines, and sort of make them better without having to go too deep on CUDA or other internals. After that point, you have to think about like what exactly is it that the GPU is doing. During token generation, what's basically happening is every time you do a forward pass through the model, you need to take the model's weights, which are located in the high bandwidth memory of the GPU, and bring basically every single weight into the streaming multiprocessors, operate on it, and produce an output. Basically, roughly speaking, for each weight, you need to bring it in, multiply with something, and accumulate it with something else. So you have one load and two arithmetic operations per parameter. That's like that's my like napkin math Feynman estimation tool. So this is the reason, as was alluded previously, why throughput oriented things are a lot better. If you are only doing two arithmetic operations per input, then you are you're very far off from the optimal arithmetic intensity, the optimal like number of operations per memory load for GPUs, which is like in the hundreds or even low thousands for contemporary hardware. And so that means you're going to be like limited in your total throughput by the memory loading operations and not by the actual arithmetic. So detailed explanations of this in our GPU glossary, the performance section, talks about this and yeah, has like numbers and other things. So the fundamentals, like one solution to this, use a better GPU. You get you increase the memory bandwidth. You'll be able to load all the weights faster. There's also a bunch of architectural things on the model level that people are doing. There's a lot of focus on this with sparse attention, with less so with sparse attention, sorry, with mixture of experts models and other forms of sparsity. But fundamentally, like going for a bigger GPU is one of like easy knobs you have to pull on this. The trick is that you need optimized kernels for that GPU to actually hit those limits, and especially for the like memory bound settings, the open source kernels aren't always like hitting the maximum performance that they can. So we've been doing a bunch of PRs to flash attention for to make it better for that. So the PRs are linked in the slides if you want to check them out. There's some cool stuff in there. We also talk about the overall architecture of flash attention 4 in that blog post. But there's like a much better thing to do than for online work with online workloads, which is to try to do more work for every forward pass that you do. And the primary way that people do this is speculative decoding. So you have some cheap system that speculates or guesses what the next couple tokens are going to be, and then you pass all of them through the LLM at the same time. And that allows you to amortize the weight loading effort over a lot more work. And you can set this up such that you still get the exact same probability distribution over tokens, and so the same model behavior as you would get if you ran the target LLM auto regressively one token at a time, but you get much faster. And this is huge. This is like the sine qua non of serving LLM inference online. It's critical you get like very easy 2x, 3x, 4x speedups and even faster ones if you work harder. Great question from Max. How do you time the inference for the speculator and the target LLM? This is one of the things that's really tricky to get that to avoid host overhead on, because you want to sort of you want to make sure that you are not slowing down your target model inference with speculator model inference. So that's, I think if you look at, I think maybe the PRs in that blog post aren't as much about the speculator, but that's definitely a really key target for improving performance. The basic answer is that you want to make there's a trade-off between how good the speculator is and how expensive it is to run, and you want to balance those to get overall improved system performance. I think people lean for super cheap um, uh, speculators and really low overhead for speculators to try and make sure that they get as much sort of like juice out of them. So one thing I want to clarify based on a question from Levante, the speculator does not have to be a language model. Speculator is anything that produces tokens. You could do it yourself if you wanted. You'd probably, like, speculating tokens is pretty hard, so you'd probably not be good at it. But it could be a human if you're crazy, or if you're less crazy, it could just be something that looks up previous sequences in the prompt and then guesses that they're going to be repeated. That's like an n-gram speculator. You can also, the thing where people have landed um, is to take the activations of the model, many of which you're already storing in a KV cache, take the activations of the model and pass them through a very small, cheap model that can then guess what the next tokens are. This is actually built into some models like GLM5 as multi-token predictions. So these are like sort of extra heads on the model. The multi-token prediction built into models like GLM 4.7, DeepSeek, GLM5. It's really great. It's built into the model. You should turn it on always, like unless you have a really good reason not to. Maybe some throughput workloads. I guess you wouldn't want to turn that on. The other thing is that you get a lot of lift when you train a custom speculator on your own traffic, especially like the narrower your use case is and the more sort of like structured, sort of like specific tool calling, for instance, that you do. If you have like an agent framework with a very specific sort of like chassis prompt structure, the speculator can get really good at that and then rip through those tokens like and get like 5, 6, 7 tokens right at a time. And so the one direction of that we're excited about is diffusion language models for this. They are really good at like maximizing quality speculation for compute at the target quality that speculators have. So we work closely with the DFlash folks to make sure that they got to help them achieve the speedups that they report in their paper. Those benchmarks were run by us on Modal, and they report what's that? Yeah, 5x speedups in a math domain for small models at concurrency 1. And yeah, so we're excited about this. We also expect this to become like a really critical part of large scale production serving, to sort of automatically train these speculators. Ideally using modal infrastructure, because we also support training, not just inference. Yeah. So the yeah, I guess I will answer Cheyon's question. Oh yeah, we're at time, so I'm going to keep going because this session is recorded, and that way the stuff that I talk about will still end up in the recording that's going to be available afterwards. You should get a link both to the recording here in the Contrast webinar platform and also on YouTube. So you'll be able to see this if you got to go, if you got a hard stop. Thanks for joining, and I hope to see you at the next one of these webinars. But for everybody else, let's keep going. Oh, yeah, sorry, I was going to answer Cheyon's question before going further. So yeah, Cheyon's pointing out that some of the benchmarks that are out there from artificial analysis and others indicate that 8x running on like a single node for Hopper versus Blackwell, you don't get a huge lift. What's the reason there? I think the basic answer is it's about kernel quality, and we found that like our getting the FA4 kernel to be good for decode and at the target concurrencies in those benchmarks um, was really critical for actually making good use of the Blackwell hardware. Other folks are also working on Blackwell kernels in a bunch of different ways and integrating them into the rest of the software stack. So I expect that we see that rapidly changing. The only place where it's like a huge win right now today is if you do your matmuls in 4-bit floating point, which is like GPTOSS 120B is and NVIDIA's Nematron models are, I think, the place where you'll see that. But I expect that to come to more models over time. Like I'm pretty excited about a GLM5 NVFP4 quantization. I think that'll really rip on Blackwell. All right. So we talked a lot about the inference system narrowly, like the tokens in, tokens out part. That is one part that you need to make fast. The other thing you need to worry about is like network latency, communication from clients to the system and then back to the clients. Like the good news, or maybe it's bad news, is networks are already operating at pretty large fractions of the speed of light. Like if you are especially if you're thinking about talking to clients that are like across an ocean, there are limits to the to how quickly a photon can get from one to the other, and from like your client to your server and then back. And networks do operate at like 50% or more of that limit, but that's not quite fast enough. The solution to this is to sort of distribute and if you have global clients, to like put your replicas all close to your clients. So Modal can help you like scale out onto GPUs all around the world so you can serve all those clients effectively. We also have if you're like interested in this, come talk to us about our experimental Flash or HTTP server features for ultra low latency, ultra low overhead, and edge distribution. So then the last piece is startup latency, like how long. So we talked about the system itself. We talked about getting things in and out of the system. Unless your load is very steady, if you want to achieve if you want to achieve both hitting your SLAs and controlling costs, you're going to need to spin up and down new replicas of your LLM inference service. And that is something that, if you aren't careful, can be extremely slow. And that's something we've optimized quite a bit on Modal. So the like naive baseline for this is like tens of minutes or longer. You need to acquire resources from a cloud, and then you need to initialize a container to run your service in. That container image needs to be loaded. We've done a lot of work on like quickly loading container images. So that shows. I actually kind of skipped that in this slide here, but that helps keep that container initialization in the top left there down to just like seconds. So we have a combination of eager and lazy loading of the container image, and like caching and content-based addressing for the container image. So I'm actually giving a talk at GTC in a month. If you'll be there, would love to meet you there, and I'll be talking a lot about this system. And how we optimize this performance. So that cuts out like tens of minutes. That cuts out minutes from your startup. The other piece is you're going to need to get the model weights loaded onto this new replica. Especially if you're doing edge deployment, that can be really tricky. You're frequently going to be going over the internet, we're able to saturate that like typical like Ethernet bandwidths of like a couple gigabytes a second with modal volumes, our distributed storage solution. So that can get you that's the difference between loading a 100 gigabyte model in a minute or 10 minutes. So we can make that about 10 times faster. So then the last piece that you have is like then setting up your LM inference engine. This takes time. There's JIT compilation, engine configuration, all kinds of stuff that SGLang and VLLM do when you spin them up. That one's tricky because a lot of these things can't be like written to disk and then retrieved, because they're in-memory data structures, a lot of them, and they're like specific to the hardware that you're deploying it on. So we have a feature that solves this problem, GPU snapshots. We can skip basically after the first time that a replica is deployed onto like a new setting, we can skip the engine start in every future scale up. And so that can take something that runs for on the order of like a couple of minutes and make it run in tens of seconds. And so then the like tentpole latency that you have left is model weight loading time. And so then you can kind of like estimate your cold start times by adding like a 50% buffer or something onto 1 to 2 gigabytes per second, and multiplied by the or divided by the number of gigabytes in the model weights that you need to load. So this GPU snapshot feature is, again, like a big focus of the talk I'll give at GTC, which will also be made available online by NVIDIA afterwards. So if you're interested in that, check out our blog post on it, or stay tuned for that talk. Oh yeah, sorry. Speaking of our blog post on that topic, I knew I had it somewhere. We have a bunch of benchmarks of it and information about how it works. The LLM workloads document also shares code for how to integrate GPU snapshots with VLM and SGLang. Takes a little doing. But the upshot that you can see here is that you have this like 10x reduction in your median startup time, and your P99 startup time starts to look like your like P50 startup time, or your P0 startup time even, without snapshots. So this is especially good for, I would say, models up to the scale of like tens of gigabytes of parameters. We're looking into ways to extend it to larger models. Cool. So rapid tour of that stuff. Lots more information in the LM workloads document, including a bunch of links and additional resources and context around all this stuff that I just shared. So definitely check that out. Share it with folks who couldn't attend this webinar. And as we wrap up here, want to just like reemphasize, we're really excited about this new modal research project of our of this free concurrency 1 endpoint for GLM5. Please try it out. Let us know. We've been dogfooding it, using it in our open codes and open clause and cursors and what have you. Would love to hear how it goes for you. Thanks also to the folks in the chat for the positive response. If you if you run into any issues, just email us at or contact us in the Modal Slack, modal.com/Slack. Happy to help you work through any issues. Great. Then I will. Thank you so much for coming. We'll be doing more of these webinars, and we look forward to sharing more of the things we've been working on at Modal with our both internally and with our customers. I think our next webinar, we've picked the topic. I think we're going to be talking about sandboxes for executing your agent code, or whatever else you want to do with a safe, secure cloud container. So definitely come check that out if you want to, say, run a large background asynchronous coding agent that can, write PRs to update your repo or review PRs as they come in. Yeah, you can serve the whole thing off of Modal and have a Claude Code web or whatever at home. All right, thank you so much, and I look forward to seeing you at future webinars and around in the space. Thank you. Bye-bye.